Okay, so you probably picture an atom like a tiny solar system, right? Well, for a long time, the smartest people on the planet had a totally different idea. We're going to dive into the wild story of one experiment that just blew that whole concept apart and changed, well, everything.
So what's really inside an atom? It feels like such a basic question today, but a little over 100 years ago, scientists were pretty confident they had the answer. And oh boy, were they in for a surprise.
Okay, so to really get why this was such a huge deal, we've got to go back to what everyone thought was true. Back at the beginning of the 1900s, the scientific community had this very tidy and, frankly, comfortable picture of the atom.
It was called the plum pudding model. Yeah, seriously. Imagine a soft, kind of mushy ball of positive stuff and then stuck inside of these little negative electrons, like raisins in a pudding. Super simple, right? Everything was uniform, predictable, a nice, neat little package for the building blocks of the entire universe.
But science is never that tidy for long. It just takes one person, one curious mind, to look at the accepted truth and ask, is that really it? And that one question can change the world, which is pretty much exactly what happened next.
And here's our hero, a scientist named Ernest Rutherford. He looked at this whole plum pudding idea, this nice, simple atom, and he just wasn't buying it. He thought, is it really just a blob? Is that all there is to it? So he designed an experiment to find out for sure. An experiment that would go down in history.
And the setup for this experiment, honestly, it was brilliant in its simplicity. So step one, you've got a source that shoots out these tiny, super fast, positively charged particles. They're called alpha particles. Think of them like microscopic cannonballs. Step two, you need a target. He used an incredibly thin sheet of gold foil. I mean, so thin it was just a few atoms thick. And finally, step three, a detector screen wrapped around the foil to basically act like a catcher's mitt and show where all those little cannonballs ended up.
Now, based on that whole plum pudding idea, Rutherford and his team were pretty sure they knew what was going to happen. This was supposed to be a simple confirmation, just proving what they already thought they knew.
And their logic made perfect sense. If an atom is just this soft, squishy pudding, then these high-speed particles should just rip right through it, no problem. I mean, it's like firing a bullet through a puff of smoke. Sure, maybe a few would get nudged off course just a tiny, tiny bit, but pretty much all of them should have gone straight through. But that is not what happened. Not even a little bit. I mean, yeah, most of the particles did go straight through exactly like they predicted. But then, some of them got deflected at these crazy sharp angles. And here's the part that just blew everyone's mind. A few of them, just a tiny fraction, like 1 in 8,000, hit that gold foil and bounced almost straight back.
Rutherford himself had the perfect way to describe how insane this was. He said it was as if you fired a cannonball at a piece of tissue paper and it came back and hit you. Just think about that for a second. It shouldn't happen. It's impossible. And that impossible result could only mean one thing. The plum pudding model wasn't just a little wrong. It was completely, totally, fundamentally wrong.
So, a result like that, a result that just defied all logic, it pointed to a radical new idea. There had to be something unbelievably tiny, incredibly dense, and really powerful hiding somewhere inside that atom. It was time to throw out the old rulebook and write a new one. And here was the big aha moment. For one of those positive alpha particles to bounce straight back, it must have hit something that was also really, really positive and super dense. This led Rutherford to a conclusion that was just staggering. The atom must be almost entirely empty space. And right at the very center of that emptiness, there had to be a tiny superdense core that packed in all the positive charge and almost all of the atom's weight. He gave it a name, the nucleus.
So just like that, the entire picture of the atom was turned on its head. We went from thinking of it as a solidish, uniform pudding to this new idea of a tiny, dense core, a nucleus, at the center of a whole lot of empty space, with electrons way out on the edges. It wasn't just a small tweak. The fundamental picture of matter itself had changed overnight.
And this wasn't just some small update to a textbook. No way. Discovering the nucleus kicked off a brand new age for science. This new idea, officially, is called the nuclear model of the atom, and it is a huge deal. It's basically the granddaddy of all the atomic models we have now. The entire foundation of modern physics and chemistry is built on this one discovery.
You can really think of 1911 as a dividing line in history. Before that experiment, the atom was a blob. After it, the door was blown wide open for everything that followed. Quantum mechanics, nuclear power, you name it. Our entire understanding of the world at the smallest scales started right here.
So what's the big takeaway from all this? It's that one single, brilliantly simple experiment completely changed how we see reality. It showed us that the solid world all around us, this desk, your chair, you, is made of atoms that are almost entirely empty space, with a powerful little core holding it all together.
Which, of course, leads to one last kind of mind-bending question, doesn't it? If atoms are mostly empty space, and you're made of atoms, and the wall is made of atoms, why can't you just walk straight through it? Well, that's a whole other can of worms, and a story for another day.